You know the feeling of standing outside on a clear night, looking up and seeing stars. That feeling, that quiet, slightly unnerving sense of something enormous above you, is real. The universe is enormous. You already know this. You have been told it your whole life. But here is what no one tells you. Something is moving out there. Something so large it does not have a name yet. Something so powerful it is pulling entire clusters of galaxies, hundreds of thousands of galaxies at a time, all in the same direction, all at the same speed, all toward the same point. And that point is not somewhere inside the universe we can see. It is beyond the edge of everything we will ever be able to observe. Think about what that means for a moment. We have built telescopes that can see 13 billion light-years in every direction, so we have mapped the cosmic microwave background, the faint afterglow of the Big Bang itself, pressed into the sky like a fingerprint. We have tracked the movement of galaxy clusters the size of which the human mind cannot genuinely comprehend. And yet, something on the other side of all of that is pulling the universe sideways. Astronomers call it dark flow, and no one knows what it is. In 2008, a cosmologist named Alexander Kashlinsky and his team at NASA were studying the motion of galaxy clusters using the most detailed maps available of the cosmic microwave background. They were not looking for anything unusual, they were doing routine science. But what they found was anything but routine. Thousands of galaxy clusters, spread across billions of light-years, were all drifting in the same direction, not randomly, not in scattered patterns the way you might expect from a universe expanding equally in all directions. Together, coherently, moving toward a single region of the sky, consistently, persistently. This was not supposed to happen. In the standard model of cosmology, the universe expands uniformly. Matter should be pulled in all directions more or less equally at the very largest scales. There should be no single preferred direction. There should be no enormous coherent drift. And yet there it was. The flow was not subtle either. The clusters were moving at roughly 600 to 1,000 kilometers per second. That is fast enough to cross the distance between the Earth and the Moon in less than 7 minutes, across a volume of space containing thousands of galaxies, all heading the same way. Scientists checked the data, then checked it again. And they looked for instrumental errors. They looked for contamination in the microwave background maps. They ruled out known structures, the Great Attractor, the Shapley supercluster, the massive gravitational concentrations we already knew about. Nothing inside the observable universe was large enough or massive enough to account for it. Whatever is pulling these galaxy clusters has to be outside the region of space we can see. It has to be beyond our cosmic horizon, beyond the boundary past which light has never had enough time in the entire history of the universe to reach us. We are being pulled by something we cannot see, cannot measure directly, and may never reach. That is where we are starting today. To understand what dark flow actually means, to feel the weight of it properly, you need to first understand the scale of what is moving. Start small, or at least start with something that feels small by comparison. The Milky Way galaxy is roughly 100,000 light-years across. 1 light-year is about 9.46 trillion kilometers, so the Milky Way from one edge to the other stretches approximately 946 quadrillion kilometers. If you built a scale model where that distance was compressed to the width of a human hair, the distance from the Earth to the Sun would be roughly 1/10,000th of a nanometer, smaller than an atom, and that is just our galaxy. Now step back further. The Milky Way sits in a small cluster of galaxies called the Local Group, about 50 galaxies in total, all gravitationally bound to each other, are spread across about 10 million light-years. Think of it as a small neighborhood. That neighborhood sits inside a larger structure called the Virgo supercluster, which contains dozens of galaxy groups and stretches roughly 110 million light-years across. But even the Virgo supercluster is small. In 2014, astronomers redrawn our local cosmic map and identified a structure called Laniakea, a supercluster of superclusters containing roughly 100,000 galaxies stretching 520 million light-years across, with a total mass of approximately 100 quadrillion times the mass of the Sun. The entire Virgo supercluster, the one that contains us, sits in one small corner of Laniakea. Laniakea means immeasurable heaven in Hawaiian, and Laniakea itself is small compared to what comes next. On the observable universe, the full sphere of space from which light has had enough time to reach us since the Big Bang spans roughly 93 billion light-years in diameter. Inside that sphere, there are an estimated 2 trillion galaxies, not 2 trillion stars, 2 trillion entire galaxies. Now, inside all of that, inside this staggering, almost incomprehensible volume of space, thousands of galaxy clusters are all moving in the same direction. Here is the gut punch. The clusters involved in the dark flow phenomenon are not close together. They are spread across hundreds of millions of light-years of space. The observable universe is not a rigid, motionless thing. It moves, it expands. Everything inside it is in motion. But the motion of these clusters is not random. It is not the expected motion of expansion. It is a coherent, directed drift, the way iron filings on a sheet of paper all point the same direction when you hold a magnet underneath. Something is the magnet. To generate a gravitational pull strong enough to move thousands of galaxy clusters consistently across these distances, the source has to be almost unimaginably massive. Theoretical calculations suggest the structure responsible could be a concentration of matter many times larger than the observable universe itself, a primordial inhomogeneity, a lump in the distribution of matter that formed in the very early universe, before the regions of space we can observe today had even become causally disconnected from each other. In other words, before our region of the universe was its own region, before our cosmic horizon was a horizon at all. The theory behind this goes by the name of inflation. In the first fraction of a second after the Big Bang, the universe expanded at a rate that staggers comprehension, from something smaller than a proton to something roughly the size of a grapefruit in an interval of time that makes a billionth of a second feel geological. During that expansion, quantum fluctuations, tiny random variations in energy density, were stretched to cosmic scales. Most of those fluctuations became the seeds of galaxies, the slight overdensities that gravity eventually pulled into stars and planets and everything we know. But some of those fluctuations, if inflation lasted long enough, could have been stretched to scales far larger than our observable universe. They could be sitting out there right now beyond our horizon as mountains of mass compared to which Laniakea is a pebble, and we would have no way to see them. We would only know they were there by their pull. The dark flow, if it is real, is essentially a gravitational whisper from the universe we cannot see. Kashlinsky's team continued refining their measurements through the 2010s and the signal persisted. Other researchers challenged it. Some studies using different data sets failed to detect it. The debate is not settled. Science rarely settles quickly when the stakes are this high. But here is the question that should stay with you. If it is real, if something truly enormous is pulling the visible universe sideways from somewhere beyond the edge of everything we have ever seen, then what does that make the universe? Not a closed system, not the whole story, something more like a room, and the door is closed. See, and something large is pressing against it from the other side. There is a concept in cosmology called the cosmic horizon. It is the boundary beyond which we cannot see, not because there is nothing there, but because the universe has only existed for about 13.8 billion years and light travels at a finite speed. Anything beyond that boundary has simply not had enough time to send us a signal. The light is on its way. It just has not arrived yet. And because the universe is expanding, and expanding faster the farther away things are, some of that light will never arrive. The horizon is not just a temporary blind spot. For some regions of space, it is permanent. This means the universe is, in a precise and measurable sense, larger than we will ever be able to see. How much larger? We do not know. See, inflation models suggest it could be millions of times larger than the observable sphere. Some versions of the theory produce a universe effectively infinite in extent. There is no upper bound. The mathematics allows it. You are sitting at the center of a sphere of knowable space, surrounded by an ocean of unknowable space, and something in that ocean may be large enough to reach in and pull on what you can see. Now think about what the human species has done so far. We have been making tools for roughly 3.3 million years. We have had writing for about 5,000 years. We have had telescopes for around 400 years. We have had space-based observatories for about 60 years. In the span of cosmic time, we appeared yesterday. We started looking up seriously about 3 seconds ago, and in those 3 seconds, we have managed to detect what might be a gravitational signal from a structure that exists beyond the boundary of everything we can ever observe. We found it by measuring the temperature fluctuations in ancient light, cross-referenced against the bulk motion of galaxy clusters, and running the numbers until the numbers told us something strange. That is not a small thing. There is a version of this discovery that feels terrifying. A version where the response is, we are tiny, we are being pulled by forces we cannot name, we are specks in a universe that does not know we exist. That version is not wrong, exactly. But there is another version. We are the part of the universe that figured this out, not another species on another planet. Us, here, now. How with the instruments we had and the mathematics we developed and the willingness to sit with uncomfortable data rather than dismiss it. The universe does not care about us, that is true, but we are made of the universe, and we are the part of it that cares. We are matter that somehow became curious about matter. We are the cosmos looking at itself, confused and awed by what it sees. Dark flow, if it is real, and the science is still being tested, would mean that our observable universe is not an island. It is a single room in a building of unknown size, and we have been sitting in that room, looking at the walls, constructing careful and beautiful maps of everything inside them. And then one day we felt the floor tilt. That tilt might be nothing. A measurement artifact. An error in the models. E-science has been wrong before and will be wrong again, and the researchers who dispute Koszaliński's findings are doing exactly what science requires, pushing back, demanding better evidence, refusing to accept the extraordinary without extraordinary proof. But if the floor is tilting, if something truly sits out there, beyond the last photon we will ever receive, massive beyond comprehension, older than any structure we have mapped, pulling on the part of the universe we can see the way a tide pulls on a shore, then we are not at the edge of the universe looking out into emptiness. We are somewhere in the middle of something we have barely begun to understand, and the pull continues, quietly, in a direction we cannot look.